In this lecture, we'll go over the algorithm for constructing circuits.
The circuit that we did in the last lecture was simply an example and wasn't really meant to carry out any meaningful operations. To create circuits that perform useful arithmetic and logical functions, we need a way to convert a description of a circuit's desired behavior into a circuit diagram, which would be composed of AND gates, OR gates, and NOT gates. And these gates would do exactly what we wanted to do. Now, there are several different types of circuit construction algorithms to accomplish this task. And what we're going to be doing here is describing one such technique, which is called the sum of products algorithm. This allows us to design circuits. So there are 4 steps that are involved with this particular algorithm. The first step is that we're going to construct a truth table. The second step is that we're going to construct a portion of the expression, or we call it a sub-expression, using just the AND and NOT gates. And then we're going to combine the sub-expression using OR gates. And then finally, we're going to actually produce the circuit diagram. The first step is that we need to determine how the circuit should behave under all possible circumstances. That is, we need to determine the binary value that should appear on each output line of the circuit for every possible combination of inputs. Now, this information can be organized using a truth table. So if a circuit has n input lines, and if each input line can be either a 0 or a 1, then that means that we have 2 to the power n combinations of input values. And the truth table, well, it's just going to have 2 to the n power rows. So for each output of the circuit, we must specify the desired output value for every row in the truth table. So for example, let's say a circuit has 3 inputs, and we'll label them as A, B, and C. That means our truth table is going to have 2 to the 3rd power, or 8 input combinations. And let's just suppose for this particular case that we're going to have 2 outputs, which we'll label as output 1 and output 2. So here is a possible truth table that we can have. So the reason why we have 8 combinations is we have 8 different ways of seeing all the different 1s and 0s for A, B, and C. So we have 1, 1, 1, 1, 1, 0, 1, 0, 1, and so forth. But we have all the possible inputs for A, B, and C, and then we have these 2 different outputs. So this truth table would specify the value of each of the 2 output lines for every one of the 8 possible combinations of inputs. And we'll use this example to show the other steps of the algorithm. For the next step, we're going to choose any one output column of the truth table that we built in the previous step. And then we'll scan down that particular column. Every place that you find a 1 in that output column, you're going to build a Boolean sub-expression that produces the value for exactly that combination of input values and no other. So to build this sub-expression, you examine the value at each input for this specific case. If the input is a 1, you use that input value directly in your sub-expression. Now, if the input is a 0, you'll first take the NOT of that input, where you would change it from a 0 to a 1, because we want to make them 1. So change it from a 0 to a 1, and then you'll use that complemented input value in your sub-expression. So now you have an input sequence of all 1s. So if we modify this by combining them with an AND operation, now you have to do this 2 at a time. You can't just combine all of them as one giant AND statement. You have to do AND 2 of them, and then AND the next one, and AND the next one. But if you bring them all together using ANDs, then the output value has to be a 1. Let's take a look at our truth table again. And for this example, we'll just take a look at only output 1, or out 1. So if we scan down this entire column, we'll see that we have 2 different 1s, which means we'll need 2 different sub-expressions to handle these 1s. So let's take a look at the first one. So we'll take a look at this one right here. So in this row, if we take a look at A, B, and C, only the C is 0. So you see that we have this C right here. So this is 0, which means we need to use the NOT operator on it and turning it from 0 to 1. Now the A and B in this row are already 1, So we don't need to make any modifications to them, we just leave them alone. So what we should now have are 3 different ones, and we can put them all together. So when we combine that using the AND operator, we would get A and B and not C. And that would produce our 1 for the output. Now for the second sub-expression, so that's down here, we'll get not A and B and not C. Well, how do we do that? Well, notice that the A and the C both have zeros in this row, which means we need to apply the not operator for both A and C. B is already 1, so we're going to leave that alone. So that's how we would get not A and B and not C. We'll now take each of the sub-expressions that we produced in the last step and combine them. Now we're going to do this 2 at a time, and we're going to use OR gates. So what this means is that each of the individual sub-expressions produces a 1 for exactly one particular case where the truth table output is a 1. So the OR of the output of all of them produces a 1 in each case where the truth table has a 1 and in no other case. So what that means is the Boolean expression produced in this step implements exactly the function described in the output column of the truth table on which we're working. So if we use our recurring example, remember that we had 2 sub-expressions from the last step. So all we have to do is just combine them by using the OR gate. So this would give us not A and B and not C, or A and B and not C. The last step is to construct our circuit diagram. So if we're going to do this, we need to convert the Boolean expressions that were produced at the end of the last step into a circuit diagram. So we're going to be using the AND gates, the OR gates, and the NOT gates to implement the AND, OR, and NOT operators that appeared in the Boolean expressions. So this circuit diagram is going to produce output that was described in the corresponding column of the truth table that we did in the first step. So each logic gate that we're going to put in here is going to correspond to that logic operator, and the result is going to be identical to what we had in our truth table. So here is the resulting circuit diagram for output 1. And if you don't believe me, let's just kind of walk through this and actually see that it is our expression that we had from before. So let's follow A first. So we have A that goes through this NOT gate, and that gives us not A. So there's not A. And then we have B that goes through the same AND gate. So we have B right here. That looks a little bit better. Kind of. Okay, there's our B. So there's our gate for not A and B. So we got that part. Let's go down to C real quick. So we have C that goes through a NOT gate. So that means that we have a NOT C here. So we'll put a bar right there. So that means that the first 2 AND gates up top. So now this whole part, this part right here, takes care of NOT A and B and NOT C. So all this takes care of, yeah, so we mentioned NOT A and B, if I can draw this, and not C. So that whole gate takes care of that part. Now let's take care of the bottom part of our circuit. So we have A down here because it didn't go through the NOT gate, so we follow A down to here. So this is just normal A. And then we have B right here. So we have A and B for this gate. And then if we go to the next AND gate, we see from the NOT C, we have NOT C right here. So this gate right here takes care of A and B and NOT C. So then we combine those two with our OR gate here. So we have NOT A and B and NOT C, or A and B and NOT C, which is exactly what our expression was. So this will definitely give us the output from that column that we had in our truth table. So here is the complete algorithm for using the sum of products algorithm. So in our example, we only dealt with one output column, but we would have to do it for each output column. So the first step is that we're going to construct our truth table that describes the behavior of the desired circuit. And then as long as we still have an output column to process, we'll do steps 3 through 6. So we would pick the output column. We'll do a sub-expression construction using the and not gates. We would then combine the sub-expressions using the OR gates, and then we would just construct our actual circuit diagram by replacing the and, or, and not operators with and, or, and not logic gates. And then we just repeat this for each output column, and then we combine it all and we would have our entire circuit.